At the very heart of the study of real analysis lies the notion of differentiability and integration. And these two notions are tied together by the very beautiful fundamental theorem of calculus. Complex analysis also, the things are quite similar. At the very heart of the study of complex analysis, the notion of complex differentiability and complex line integrals lie. And they are also tied together by a variant of the fundamental theorem of calculus. There is a further variant of this fundamental theorem called the Cauchy's theorem, which lends certain amount of rigidity to complex differentiable functions, thereby making the theory very beautiful. In this lecture, we will define complex differentiability and explore some of its properties. So, let us begin by recalling the notion of differentiability over the real numbers. So, recall that a function f from u to r is said to be differentiable at a point. Oh, so what is u? U contained in R. At a point x naught in u if x naught is an interior point of u and the following limit exists, and limit x going to x naught and x in u minus x naught of f of x minus f of x naught by x minus x naught exists. If this limit exists, we say that a function f, a real valued function f defined on u, is differentiable at the point x naught. We then say that okay, let's denote this. The limit is denoted by f prime at x0, and f prime of x0 is said to be the derivative of f at x naught, which is called the derivative of f at x naught. And if f happens to be differentiable at every point x in u, then we say that f is differentiable on u. Let us somehow mimic this definition. Let us adapt this definition to the complex variable setting. We are going to be defining complex differentiability very similarly. So, complex differentiability. So, let omega be a subset of C and f be a map from omega into C. Let us consider a complex valued function on omega. We say that f is complex differentiable. I am going to adapt the definition verbatim, in fact, by making the relevant changes. We say that f is complex differentiable at a point z naught in omega if z naught is an interior point and the following limit exists, and limit z going to z naught, where z is in omega minus z naught, if this okay, which limit? F of z minus f of z naught by z minus z naught exists. If this limit exists, then we say that f is complex differentiable at the point z naught. The limit is denoted by f prime at z naught, or as df by dz at z naught. So remember that f prime at z naught is a complex number, or df by dz at z naught is a complex number. And if f is differentiable, or rather complex differentiable, I should be very careful. If f is complex differentiable at every point z naught, at every point z in omega, then we say that f is holomorphic on omega. We say that f is, let me say, complex differentiable on omega, or holomorphic on omega. I will slowly start using that word holomorphic on omega, or holomorphic on omega. There are variants of this particular definition. The first variant would be an epsilon delta variant. So how do we capture that? We say that f is differentiable, complex differentiable at z naught if there exists a complex number f prime at z naught in C such that absolute, given epsilon positive and given epsilon positive, there exists delta positive such that the disk of radius delta around z naught is contained in omega, and absolute value of f of z minus f of z naught by z minus z naught minus f prime of z naught is less than epsilon whenever 0 is less than mod of z minus z naught is less than delta. If you notice carefully, we have just rewritten the definition above in the epsilon delta setting, which you will be familiar with. So another variant of the definition is in terms of approximate linearization. We say that f is complex differentiable at z naught. So the setting is the same. I am not writing the setting again and again. F is a complex valued function from omega into C, and z naught is some interior point in omega. F is complex differentiable at z naught if there exists a complex number, if there exists f prime at z naught in C and E of such that f of z is equal to f of z naught plus f prime at z naught times z minus z naught plus small o of z minus z naught, where small o of z minus z naught is equal to z minus z naught times E of z, where E of z goes to 0 as z goes to z naught. So notice that the limit is being taken along any complex, any sequence of complex numbers converging to z naught. So this is very similar to how we had defined the differentiability on the real line, and some of the consequences there immediately carry forward here as well. So for example, if a function is complex differentiable at a point z naught, then the function is necessarily continuous. Let me make that observation, maybe a lemma. If f from omega to C is complex differentiable at omega contained in C at the point z naught in omega, then f is continuous at omega at z naught. The proof is immediate because if you write down the linearization, approximate linearization here, for example, what do we have? We have f of z minus f of z naught is f prime of z naught times z minus z naught plus o of z minus z naught, and we know that as z goes to z naught, o of z minus z naught goes to 0. And f prime of z naught is fixed, therefore f of z minus f of z naught goes to 0 as z goes to z naught, and therefore f has to be continuous at z naught. So let me not write down a proof of this, it's just the same proof as in the real variable setting, one variable real differentiable functions. In fact, in the complex setting, we get far higher regularity, but we will come to that later. Let's not worry about it yet. Let's now look at an example. Let f of z be equal to z to the power n be defined on the complex plane. Omega here in this case is the entire complex plane. The function is quite straightforward. It is f of z is equal to z to the power n. And let's see if it is complex differentiable at a given point. Fix z naught in C, and let's see what is going to be f of z minus, for z naught equal to z naught, we have f of z minus f of z naught by z minus z naught is equal to z to the power n minus z naught to the power n by z minus z naught. Geometric series, actually you should sit down and check that this is exactly equal to z to the power n minus 1 times z naught z to the power n minus 1 plus z to the power n minus 1 times z naught n minus 2 times z naught plus up to z to the power n minus 1. This is precisely the geometric series, which you can check this inductively if you want. If you are not convinced, you can prove this inductively, that z to the power n minus z naught to the power n by z minus z naught is exactly equal to this. Now if you take limit as z goes to z naught, then this is going to be the limit of this, which is going to be z naught to the power n minus 1 plus z naught to the power n minus 1 plus up to z naught to the power n minus 1, and each of this is contributing once. There are n terms, and hence this is equal to n times z naught to the power n minus 1. So as is to be expected, the derivative, the complex derivative of z to the power n turns out to be n times z to the power n minus z at a point z naught turns out to be n times z naught to the power n minus 1. So as is to be expected, the laws of calculus, they actually carry forward to complex differentiable functions as well. For example, the linearity property is satisfied. If you look at, so let me write that down. The laws of calculus are satisfied. So for example, the same proof actually goes through. If f comma g are functions from omega contained in C to C are complex differentiable at a point z naught, then so is f plus g with derivative, with complex derivative f prime at z naught plus g prime at z naught. This is the additive property. If C belongs to omega, if C is some complex number, and if we consider C times f, then C times f is also complex differentiable at z naught, and C times f The derivative of this at z naught is just going to be c times f prime at z naught. So the proof is exactly similar to the way we prove it in the real variable setting. So I would refer you to a proof in, say, for example, Principles of Mathematical Analysis, Rudin, and I'll request you to sit down and give a very similar proof in this complex variables setting as well. It should go through, very similar proofs should go through. Well, not just the linearity property, the product rule also holds. If f and g are maps from omega to omega, be again some subset of c into c, be complex differentiable at a point z naught in omega, then fg is complex differentiable at z naught with derivative f prime at z naught times g at z naught, the usual Leibniz rule, plus g prime at z naught times f of z naught. So the usual product rule, this is called the product rule, right? I'll call the product, it's the same thing here. The first one was linearity, right? If you have a function which is complex differentiable at a point z naught and such that g is not vanishing there, okay, quotient rule. Again, I'll leave the proof to you. It's exactly similar to the real variable setting. If f is, if both f and g from omega contained in C two complex numbers be complex differentiable at a point z naught at z naught in omega. Suppose both f and g are complex differentiable at z naught, and suppose g does not vanish at z naught, then by continuity of g does not vanish in a neighborhood of z naught, right? Then by continuity, g does not vanish in a neighborhood d of z naught. Then f by g is complex differentiable at the point z naught in D, is complex differentiable at z naught. So slowly I will stress upon the fact that the complex differentiability is a local property, and therefore when I talk about complex differentiability at x naught, when x naught is thought of as a point in D, or whether it is thought of as being complex differentiable at x naught when with x naught as a point in omega, the difference is there is no difference, it's the same. The idea of complex differentiability is a local property at a given particular point. And the quotient rule also tells us that f by g prime at x naught is exactly equal to f prime at the point. So I should not be using x naught here because I've taken the point z naught above, right? So the point here was z naught. So let me again use z naught here. F by g prime at z naught is f prime at z naught times g of z naught minus g prime of z naught times f of z naught by g of z naught square. This is the product rule. Again, the proof is going to be similar there. And finally, let me also talk about the chain rule. The chain rule is, what does the chain rule say? If you have f a function from omega into c, and suppose v is a function from, sorry, g is a function from v to c such that v is sitting inside the is inside the image of f, then if you consider g composed with f and look at the derivative, then this is going to be g prime at f of x naught times f prime at x naught. That is the statement in the real variable setting. We will be able to say a similar statement in the complex variable setting as well. So let f be a map from omega into c and be complex differentiable at a point z naught. Be complex differentiable at z naught in omega, and suppose g is a function. Suppose g is a function from, say, d into c such that g is complex differentiable at f of z naught. At f of z naught, f of omega is contained in d. Let's put this extra condition. It's a local property. If needed, we could shrink our omega to the small neighborhood where we are looking at the complex differentiability, and we can still realize the chain rule the way we need it. So suppose this condition is also there, then g composed with f is complex differentiable at z naught. And further, g composed with f prime at z naught is equal to, as is to be expected, g prime at f of z naught times f prime at z naught. Yeah, let me not skip the proof of this. I have been skipping the proof of all the elementary statements. Maybe I should give a proof of this. So the fact that f is complex differentiable at the point z naught tells us that f of z is equal to f of z naught plus z minus z naught times f prime at z naught plus O of z minus z naught, which is just z minus z naught times E1 of z, where E1 of z goes to 0 as z goes to z naught. And the fact that g is complex differentiable at f of z naught, so let f of z naught, let's call it some name, let w naught be equal to f of z naught. So we are saying that g is complex differentiable at w naught, and this is because f is complex differentiable at z naught. There x is f prime at z naught and E1 of z such that this happens. Similarly, since g is complex differentiable at w naught, there x is a number g prime at w naught, complex number, and a function E2 of w such that g of w minus g of w naught, or g of w is equal to g of w naught plus w minus w naught times g prime at w naught plus w minus w naught times E2 of w, where E2 of w goes to 0 as w goes to w naught. Now let's approach w naught through f of z, where z is a sequence. So since f is complex differentiable at z naught, it's also continuous at z naught. And hence hence f of z converges to w naught whenever z converges to z naught. So let's look at one such sequence of points z converging to z naught, and then we see that g of f of z, so that sequence is equal to g of f of z naught is precisely what w naught is, plus f of z minus f of z naught times g prime at f of z naught plus f of z minus f of z naught times e2 of f of z. Let's write it down, simplify it and write it down. This means that i.e. g of f of z minus g of f of z naught, this is equal to f of z minus f of z naught times g prime at f of z naught plus e2 of f of z. But what was f of z minus f of z naught? We already have given a characterization of this number above. We know what this is exactly equal to, as you can see here, and using that, this is going to be equal to, this is going to be equal to z minus z naught times f prime at z naught plus e1 at e1 of z. That's what f of z minus f of z naught will be, and this is going to be g prime of f of z naught plus e2 of f of z. If you look at the limit as z goes to z naught, where z is in omega minus z naught of g of f of z minus g of f of z naught by z minus z naught. This is precisely what we are interested in, isn't it? Then this is going to be equal to the limit. Let me keep this just above. This is going to be z going to z naught of f prime at z naught, which is a constant, plus e1 of z times g prime at f of z naught plus e2 of f of z. Now let's see what happens to e1 of z and e2 of z as z goes to z naught. The e1 of z term approaches 0, because as z goes to 0, e1 of z goes to 0, and because f is continuous, as z goes to z naught, f of z goes to w naught, and we know that e2 of e2 of w approaches 0 as w goes to 0, and therefore this is equal to f prime at z naught times g prime at f of z naught, and this is precisely what we had set out to prove. So as you can see, the proof is exactly like in the real variable settings. The proofs of the statements written above, they are also going to be exactly similar. Functions which are complex differentiable on the entire complex plane are called entire functions. So let me just note that down. That's a special name given to functions which are complex differentiable on the entire complex plane. Functions which are complex differentiable on C on the entire complex plane are called entire functions. So the example which I gave above, so for example, z going to z to the power n is an entire function. We just checked that above, isn't it? And now, having all the laws of calculus for complex differentiable functions as well, we can say that any polynomial in z is an entire function by using the laws of calculus above. We have p of z, which is equal to, say, a0 plus a1z plus up to a dz to the power d. This is also an entire function. Is an entire function. In fact, we know explicitly what the derivative of p at a point z naught is by the laws of calculus, isn't it? P prime at a point z naught, this is going to be equal to a1 plus 2a2 times z naught plus d z naught to the power d minus 1. This is precisely what the derivative is going to be, because we are going to use the linearity property to establish this. So the polynomials are entire functions. More examples, we also defined rational functions. So let r of z be equal to p of z by q of z. And we had noted that this was defined on a set where q does not vanish, on omega where q of z is not equal to 0. So q, remember that q is a polynomial, and because of that it will have a degree, say d, and there should be less than or equal to d roots of q, and therefore omega can be thought of as c minus finitely many points, which is an open set. Now q of z not equal to 0, by the quotient rule, r of z is a complex or holomorphic function. By the quotient rule, I will slowly start using the word holomorphic when I want to talk about the complex differentiability on an open set. So the quotient rule tells us that r of z is holomorphic on omega. We have seen a few examples. Let's also look at a few non-examples. Let's consider the function which is the conjugate. Consider f of z being equal to z bar. We'll see that this is not complex differentiable at any point. So fix a point z naught. Then what will be f of z minus f of z naught by z minus z naught? This is just going to be equal to z bar minus z naught bar by z minus z naught. So let's take z to be z naught plus h for some complex number h. So let z be equal to z naught plus h. Then what will happen is z bar is equal to z naught bar plus h bar, and therefore f of z minus f of z naught by z minus z naught, this is equal to h bar by h, where h is not equal to 0. Right, and as h goes to 0, z naught plus h goes to z. Z naught plus h goes to z naught. So we are in the right setting, right? So limit z going to z naught is going to be the same as the limit h going to 0 h bar by h. Now let's see if this limit exists. A minute's thought will tell you that based on how you approach 0, this limit will have different values. So for example, if h is taking only positive, only real values, okay, let's do this. Suppose h converges to 0 along R, then h bar is equal to h, and hence limit h going to 0 of h bar by h is equal to 1, because h bar is equal to h. And suppose this is the real axis, okay, and suppose h goes to 0 along IR, the imaginary axis, then h will be something like I times x, where x is a real number. And what will be the conjugate of ix? Ix's conjugate will just be minus ix, and then limit h going to 0 will be of h bar by h will be limit of minus 1. At every stage h bar by h will be minus 1, and this is going to be minus 1, which is not the same as the limit which we obtain when we go along the real axis. At any point z naught, at any point z naught on the complex plane you take, you fix any z naught, we can show that the limit of the ratio f of z minus f of z naught by z minus z naught does not exist. So this is a function which does not have a complex derivative at any point. Let us now consider the function f of z equal to absolute value of z square. Let's see what the situation there is. This is going to be absolute value of z square as a function is just z times z bar. So notice that there is a z bar already featuring in. You should start questioning whether this will have a valid limit. Again, let's fix a point z naught. Then f of z and z be equal to z naught plus h. Then f of z naught plus h. This is just z naught plus h times z naught plus h bar. And that's going to be equal to the absolute value of z naught square plus the absolute value of h bar plus h z0 bar plus h bar z0. So if you look at f of z naught minus plus h minus f of z naught, this is going to be equal to h bar plus h z naught bar plus h bar z naught. And if you look at the ratio of f of z minus f of z naught by z minus z naught remember is equal to h, and we have this is equal to h bar plus z naught bar plus h bar by h times z naught. And a similar argument as above tells us that along along the real axis, we have this converges to z naught bar plus z naught, and along imaginary axis, this converges to z naught bar minus z naught, and both are equal if and only if z naught is 0. So at any point away from the origin, the complex differentiability fails for this function. We will see more examples of complex differentiable functions in the form of power series. Power series are those functions which are an infinite version of polynomials. In the disk of convergence, where it does converge, polynomials and power series have many similarities. So we will look at the notion of power series in the next week.